right, remember a couple classes ago we talked about series circuits. And remember, the circuit means the electricity, the electrons need to be able to get from one end of the battery to the other in a complete loop. And for a series circuit, so that the electrons have only one path. They must go through every single one of these resistors, the light bulbs. They have no choice. And then we also noted that because the electricity has no choice but to go through every resistor has the same current because the current is the actual amount of electricity flowing. So it must flow through every resistor in a series circuit. And we got an equation. The way to find the total resistance in a series circuit is just to add up all the resistance. And we also had Ohm's law, where we could calculate current, voltage, or resistance depending on how we rearrange the equation. And then we talked about parallel circuits, where the electricity had a choice. It wasn't all forced to go through every resistor. There's a pathway, and right here, the blue one's going up through the top one, and they all have a choice. And that's the key to a parallel circuit. It's still a circuit. The electricity still needs to be able to get from one end of the battery to the other, but it just has a choice about the path it can take. Okay? And for parallel circuits, it's the voltage that's the same everywhere. So in this case, each of these light bulbs would experience the same voltage, which means the same pressure pushing the electricity through it. Okay? And to find the total equivalent resistance in a parallel circuit, we can't just add them up. We have to take the reciprocal of the sum of the reciprocals of all the resistance. And then, of course, we can still use Ohm's law to figure out what the voltage, the current, or the resistance is. But we don't draw them with light bulbs and batteries. We draw them with, this symbol here for a source or a battery and the voltage. And then we draw the resistors, these little squiggly lines. And we draw their resistance, 16 ohms, 16 ohms, and 12 ohms. And we label the resistors. Here for the parallel one, it's basically the same, except here, when you have a choice, it's always nice to draw a junction and number it. It helps keep things in order. So, and remember that you have to keep in mind that for series circuits, the current is the same everywhere, and for parallel circuits, the voltage is the same everywhere, and that series circuits have their own resistance equation. You just add them up, and parallel circuits have their resistor equation. You add up the reciprocals of each resistance, get the sum, and then take the reciprocal of that, and they all use Ohm's law. Small series circuit and a small parallel circuit. Really, those are the only types of circuits there are, except when you combine them into something called a compound circuit. Okay? But the math is still going to be the same. We're still going to analyze the circuit. Like in this case, there's a 3-volt source, and you'll see that the electrons have a choice here. They can, when they get to junction 1, they can flow through this 1 ohm resistor or through this 3 ohm resistor, and then come back together. So these two are in parallel, and then the electricity flows has another decision to make at junction 3, where it can flow through a 2 ohm resistor or a 3 ohm resistor, joins back up, and then goes to the end of the battery. So it is a loop, but we have this pair of parallel resistors, this pair of parallel resistors, and these two pairs are in series with one another. All we have is the knowledge that for a series circuit, the current is the same everywhere. For parallel circuits, the voltage is the same everywhere. And then we have two separate equations, one to find the total resistance for parallel circuits, and it's the reciprocal equation, and one for series circuits, where you just add them up. But we don't have a single equation for a compound circuit. That means that when we redraw this, break it up into a line, we have to solve it for anything where it's just parallel or just series together, and solve them separately until we get down to one equivalent resistor. Then we can use Ohm's law, go back up through our drawings, and use Ohm's law again to find the voltage and the current at every single resistor. So first thing we're going to do is we're going to redraw this as though we're in a line. So we're going to split the battery in half, and we get to junction 1 here, and there's a choice. It can go through this 1 ohm resistor or this 3 ohm resistor. Then it has another choice after passing through one of those two. It can go through this 2 ohm resistor or this 3 ohm resistor, and then it continues on and makes its way back to the other end of the battery. Okay, now, before when we were doing series and parallel, everything we did was parallel, everything was series. But here, remember, we have this pair of parallels in series with this pair of parallels. So we cannot just apply the math and combine everything. We can only combine them if they are nothing but parallel or nothing but series. And here, these two, resistor 1 and 2, are in parallel, and there's nothing else, and these two are in parallel. So I'm going to redraw it, and I'm going to combine these two, resistor 1 and resistor 2, into one resistor, and I'm going to combine these two into one resistor using the reciprocal equation. Okay, and how I do that is I take the reciprocal of, so 1 over 1 plus 1 over 3, and then I take the reciprocal of that, and I get out my calculator, and that gives me that this is a 0.75 ohm resistor. So these two in parallel act as though they're one single 0.75 ohm resistor. These two in parallel, so 1 over 2 plus 1 over 3, that would be 0.83 repeating, and you take the reciprocal of that, and you get that that is a 1.2 ohm resistor. So these two act like a single 0.75, these two act like a single 1.2 ohm resistor. Now, we have these two left, and they are just in series. There's nothing else involved except series. So I'm going to combine those two into one resistor. Okay, and since they're in series, all I have to do is add them. So 0.75 plus 1.2 makes 1.95 ohm resistor. So this 3-volt battery feels 1.95 ohms of resistance through this entire circuit as the electrons flow from one end of the battery to the other. Okay, and now we get to do a little math. I know that, moving the paper around a little bit, I know the total voltage is 3, I know the total resistance is 1.95, and I can figure out the total current because it's voltage over resistance. So it's 3 volts over 1.95 ohms of resistance. So that gives me 1.54 amps. That's my total current. So my total current is 1.54 amps. I know that my total resistance, I already figured that out, is 1.95 ohms. And my total voltage is 3 volts. Now what I get to do is I get to go backwards up through the circuits to find out what the current and the voltage is at each and every one of these little resistors. This is where these two rules, that for series circuits, current is the same, for parallel voltage is the same. Okay, so here, this one resistor was actually 2 in series. And I know for series circuits, the current is the same. So if the current right here is 1.54, that means the current here, 1.54 amps, and the current here is 1.54 amps. Remember, the current is the actual flow of electricity, and in a series circuit, it has no choice. It has to flow through every resistor. So if it's 1.54 here, those same ones have to flow through this one. Okay, and now I have the resistance and the current. I can use Ohm's law, rearrange it for voltage, and I know that voltage is current times resistance when I rearrange that. So it's 0.75 times 1.54, so that's 1.2 volts through here. And the other one, it's still, voltage is still current times resistance, so it's 1.54 times 1.2, so this one, the voltage is 1.8 volts. Okay, and neither, I can't stop now because neither of these two is an original standalone resistor. I have to go back to the next step to complete everything. But here, this one was actually these two in parallel. And I know for parallel circuits, the voltage is the same everywhere. So the voltage here is 1.2. That means each one here, the voltage is 1.2. And for this one, this was also a set of two resistors in parallel. So if the voltage here is 1.8, that means it's 1.8 for each of these. Okay. So now I have the resistance and the voltage at each one of the four original resistors. Now I can use Ohm's law to solve for the current. It's voltage over resistance. So 1.2 over 1 is 1.2 amps. And this one is 1.2 divided by 3, or 0.4 amps. Over here, resistor 3, that would be 1.8 divided by 2, or 0.9 amps. And this one is 1.8 divided by 3, so voltage divided by resistance is 0.6 amps. Okay, now I can go ahead and fill this out. I know that the current through resistor 1 is 1.2 amps. The current through resistor 2 is 0.4 amps. Through resistor 3 is 0.9 amps. And through resistor 4, 0.6 amps. This just sort of cleans up, takes my data and puts it somewhere I can look at it neatly. And the voltage is, for the first two, is 1.2. And the voltage for 3 and 4 are 1.8 each. Okay, so now your job is to open up the first compound circuit, worksheet 1, and go through this process. Remember to keep in mind these two rules. For it, current is the same in series, parallel is the voltage is the same, and you have to use these equations separately. Get it down to one equivalent resistor using these equations. Solve for the total current, and then work your way back up through it using these. You're always going to either carry current up for series or carry voltage up for the parallel circuits, and then solve for the one you don't have.